CCP estimation, identification? We'll see. As I said, you've got your utility, you're maximizing, making your choices. You have this conditional independence assumption that we talked about last period lecture. Fair enough. We have an optimal decision rule. That's the little o. And now what we're going to do is just form this big V by integrating out over this period's epsilon. That is the social surplus function that we talked about just before break. All good? And that social surplus function comes from making the optimal decision rule from here on out, where, of course, when you make that decision, you will see those epsilons even for today, even in today's period. So now we'll define this conditional value function, just as we did in the circle model, as here's the utility that I get from the variables that the econometrician sees, as well as the discounted continuation value associated with the future. And what we're going to be doing is looking at little vj plus little epsilon j and picking that j that is the maximum, okay? If we integrate over the optimal rule, we get the conditional choice probability. Again, just going back to what happened just before break. And so the starting point for this lecture is really to note that for each j and t, there's these differences. And those differences in the conditional valuation functions have the same number. They're going to be the same number of differences in conditional valuation functions as there are conditional choice probabilities. And so there is clearly a mapping from the conditional valuation functions to the probabilities, okay? And the point of this is to say, not only is it a mapping, but it's invertible. And then we're going to exploit that. We already just did before break in a fairly straightforward example, but I'm going to argue that this is, in fact, a lot more general than that. So there are a whole lot of differences between these different conditional value functions, of course, but most of them are linear combinations of the others. And in particular, we might as well just focus on one particular, what I'll call basis function. In other words, let's compare the difference between J and big J, okay? Because all the other differences can be formed from that, all right? That's this part here. So for now, let's think about the difference between the conditional value function associated with choice J and the conditional value function associated with big J. So we know that this is just this, the choice probability is just the optimal action. What we're doing is comparing, without the triangles, Vj minus Vk, if the triangles weren't there. But what's the difference between the no triangles there with triangles there? That's just conditional valuation function of big J. So this one is just putting in, adding and subtracting the big J, okay, to get those differences. All right. And so now we just says, well, what is this thing really? We're just integrating over a bunch of regions, okay? So why don't we just integrate over the those regions, okay? Because that's really what this means. Okay. And then we'll say, well, let's have a look at the distribution of this these epsilons. differentiate that with respect to the all the epsilons to get this density, and then just rewrite the whole thing this way to get this expression, which is just another way of saying this one up here. Now let's go back to a static problem for a minute. Static problem, McFadden's style discrete choice. And if you take a choice J, you get delta J plus the epsilon. All right? Delta, a parameter. All right? Very simple McFadden discrete choice problem. So this Q then is just from the previous page. It's just instead of putting the delta V's in there, let's just put in delta J parameters for now. And in that case, what we could do is say, interpret it as a random utility model, a static random utility model, okay, in which the payoffs are just delta J plus epsilon J, okay? And then we're asking, well, what is the probability that person makes the Jth choice in this static model? Well, that's obviously just this Q from the way I've set it up, all right? And so these Qs are just, they all sum to 1. So if we're just to J minus 1, less than or equal to 1, the difference then just being the Jth choice. And we have that the conditional choice probability then is just equal to this G, where now I've just plugged in the delta V's in for the deltas, okay? Triangle V's in for the deltas. Getting a little bit confused with my deltas here, okay? So here we have a static model. We've just set it up that way. And then we say, well, okay, why not just plug in the delta V's that way too? In other words, for each X, we could do this. Follow? Here, there are no X's, or there are, but only as it comes through the G. Here, again, just through the G's. Here's the point. Let's define this vector from Q1 to Qj minus 1. Those are just the conditional choice probabilities for the static model in which people are getting these deltas. There are as many deltas as there are conditional choice probabilities. Not surprising then, maybe, that this is invertible for each t and each x. And so that really means that instead of looking at deltas, we could look at p's, which is exactly what we did in the Rust problem just before break. And I'm saying, Joe Hudson and I are saying, people agree, that this is a sufficient statistic for the differences in the value functions, in the condition, for sufficient statistic for the differences in conditional value functions. So this inversion theorem means that instead of solving for these V's, we can just write the vector of differences in V's as a function of the conditional choice probabilities. And so we can use that instead of solving through, okay? How do we interpret this Q minus 1 thing? Well, given X and the conditional choice probabilities, you've got that this thing, V little j plus the epsilon prime, say, is equal to V big j and epsilon big J prime when they're indifferent between the two. Okay? In other words, if you're indifferent between little j and big J, it must be true that this equation satisfied. Remember I said that for the case in which we had no unobservables, that they had to be indifferent if they equalized. So that's the kind of the threshold at which they're indifferent. And so what that is saying is that the difference between the V's must be the difference between these two epsilons when you're indifferent. In other words, when you've got a pair of epsilons such that you're indifferent between those choices, that gives you the Q minus 1. So that's a way of thinking about what this Q minus 1 actually is in terms of the economics, underlying economics of the problem. So more generally, if we took this Q minus 1 function, it is really a way of saying these are the set of epsilons that make you indifferent between all the choices. It's not something that we're going to use really, but it is something that is a way of thinking about what you end up with when you write down this Q minus 1 function. Why is this inversion theorem useful? Well, I've already given you a sort of answer to that, but I want to expand on that in this lecture. First of all, empirically tractable representations of the conditional value functions. Fast, easy ways of estimating dynamic programming problems. That's what the claim to fame is. Second thing, you can analyze identification within this framework. In other words, there's kind of a question always, is that likelihood function converging as the number of observations increases? Is that likelihood function converging to something that's flat in certain parts? In other words, does it converge to a unique optimum or not? Because if it doesn't, what you're going to see is equivalent to a multicollinearity problem in which, as you add observations, it's jumping around all over the place. Because for that extra observation, it'll pick something that's slightly different as you add an observation or two, because it's flat at the top. And so, since it's flat at the top, it means that in any finite thing, small differences in the observations are going to determine what estimate you get. So obviously you get something that's fairly flat, you get something that looks like big standard errors. Okay? So that's the sense in which asking the identification problem, asking identification, not in this, just in this setup, but in any structural model, is a pretty important problem. Okay? Do you actually end up with what I'll call point identification, or do you end up with something that is, we could call partial identification or set identification? You can work with set identification. I'm not saying you can't. I'm just saying that it's nice to know the difference when you go in and estimate a structural model, what you're doing. So, and then there's a kind of question as to, well, what about the epsilons here? Do we have to assume they're type 1 extreme value, or can we relax that? And there are different ways of thinking about relaxation. One of them is to just relax the IID distribution it comes from. And we'll talk about that just a tiny bit. There's also an issue, and I have to talk about, in the problem that I discussed, the Harold-Zerker problem, it had a very nice characteristic that once you got rid of a bus, you start the problem again. So it's called a renewal problem. And that's neat because you're always starting it again, and that makes it a little easier. Or if you knew it was going to stop or could stop, not was necessarily going to stop, but could stop in a finite amount of time, that would also be kind of nice. Because it'll turn out, you saw in the renewal problem that we talked about, you only had to look ahead one period ahead to get those conditional choice probabilities. You would look at the conditional choice probabilities right now, and then you'd look at the conditional choice probabilities of the next period, and that was enough. I was able to plug that so-called correction factor in there. Okay. Can we go any further than that and still keep it simple and manageable? And the answer is yes. And finally, I want to talk about unobserved variables, but a few of these things we'll leave till tomorrow. To get to the first part of the identification, because what I'm going to do is work through identification and then estimation, and then I'm going to give you another example or before lunch. So hope you don't fall asleep. I'm lucky I get this morning. So look at the conditional valuation function correction here, because that's going to play a pretty big role. You've got the social surplus function minus the conditional value function. In stationary settings, we could drop the subscript, of course, the T subscript. Why are we calling it that? Well, suppose that instead of taking the optimal action, suppose, just temporarily, all right? And I'm not doing this because I think the people in the model do it. I'm doing this just as a way of explaining what's going on, all right? You committed to action J regardless of your epsilon. And so in that case, your expected value lifetime utility would just be your Vj as before and the expected value of the epsilon, as opposed to a selected value of the epsilon. All right? Thinking about Hickett models, for example. So you're committing before epsilon, the disturbance vector is revealed to J. So you're going to lose something because you really should wait till you see the epsilon and then make a choice. So the difference between your social surplus problem, which is expected value that I'll get when I make the optimal choice after seeing the epsilons, versus committing to a choice now, what will be my expected value when I'm going to take the choice J now, but then in the future I'm promised to behave optimally. The difference between those two is, well, the loss, here's the loss, because this is what I get. It's just going to be, by definition, it's just going to be equal to this correction factor minus the unconditional, if you like. It's conditioned on X, but not on the J, of the epsilon J. Okay. So if it was true, and that's not true in type 1 extreme value, but if it was true that we're dealing with a normal distribution, for example, this is equal to 0 and the loss simplifies to that. And so that's why I'm calling it a conditional value function correction, just to get that notion of this is sort of what you lose if you make the wrong choice. I'm going to use this a lot in the estimation. And that's why I'm spending so much time on what seems like a pretty trivial point right now. So this is going to help us actually identify the conditional value function. Firstly, this thing is actually, this correction is actually identified. This thing here is identified, okay? So I want to prove that. Well, let's look at the difference between T and VIT. Okay, that's the definition for the psi of IT, all right? I'm just expanding it out now. I'm putting in the optimal behavior because there's the optimal behavior for this guy. And then I'm putting in the conditional value function here. This is the kind of stuff that you can go over later. But the difference between the conditional value functions is just equal to these Q things, okay? And when we're integrating over the epsilon over here, well, there we're just integrating over this region. Again, we're plugging in the Q things. We know what the Q we know what the G's are. Let's just go back to what the G's are. The G's were those distribution functions that I was talking about when I went through the derivatives and all that. So the Q's are going to have this functional form that we're imposing. And so coming back to this one, if we knew the G's, then we would know the Q's, and then everything would be in terms of just integrating over these different pieces. Here they are. There's one piece right here. Here's the other piece right here, just in terms of the Q's. Okay? So that's telling us that even though the value function itself is not identified, and there's no surprise about that, why would you ever be able to identify a utility level? Economists don't care about how happy people are. They care about the choices that they make, and those choices depend on the difference in happiness on this side versus versus this other side. So you're not going to be able to get beyond that ever. All right? Profits, value of a firm, yes. Utilities of people, okay? So this difference then between the social surplus function and the conditional value function is identified, providing you know the distribution of the epsilons conditional on X. So this is typically an assumption that we make, that we know that, and it turns out to be a pretty important assumption. The reason is that when you do the counterfactuals also going to depend on this. And so then the issue is, well, how robust is your counterfactual when you change that assumption? I don't like to admit that, but it's true. So suppose you had, for example, a nested logit. What would the correction factor be? It's just equal to this thing. What's going on here? You've got this correlation factor across the nest. If there was no correlation at all, this guy would go. Whoops. If there was no correlation, this guy would be 1, and then you would be just stuck with this gun, okay? With a nest here, you're summing over the nest. So it's a weighted average. This correction factor is a weighted average between the choice-specific thing and the nest thing as well, all right? So we can actually generalize beyond the type 1 extreme value in a fairly straightforward way, and go beyond that actually with generalized extreme value, just the same way as you can do it in static models. But for now, this is good enough. So this is going to lead us into actually identifying, or at least representing, the conditional value functions. So what we got here is the conditional value function is the utility plus discount factored discount of continuation value of next period, as before, all right? Now pick any action, K, any, all right? It doesn't have to be the optimum. This has nothing to do with what the agent does. This is what we do when we're trying to represent what's going on, okay? That's what I mean by pick any K. Because it's true for all of these Ks that we can always represent this big V in terms of the little v plus the correction factor. I just showed that before, all right? And I also showed that this psi thing is identified, all right? So now we have conditional value functions equal to little utility plus discounted value of, and then we do the same thing over here, all right? But this V is equal to a U plus a big V. Keep on going forward, roll it forward. Okay, we can do the same thing again. Substitute out this little V and then put in a big V and then go from there with another K, say. All right, that's what I mean by telescoping. And so, in fact, we can go a little bit further than that. I said pick an action, but actually we could have picked a combination of actions. It doesn't matter, because then what you're doing is saying the big V is equal to the combination of the little of all the various actions, where you put in the conditional valuation function for each of the little j actions plus the correction factor. You've now got that combination of things, okay? They're all going to equal big V. Why not do that? Actually, you don't even have to have these omegas equal to positive. You can make them negative. Not a problem, providing they sum up to 1. And in some of the stuff that I've done with Peter, and it's probably cited somewhere in the references, what we find is that to get finite dependence, you will often want to go with negative, I'm going to call them omegas. In other words, you want to put negative weights on some actions, positive weights on other. All you care about is that they sum up. Now, this is a mathematical identity. It's not like you're cheating or anything just because you put negative stuff in there, all right? The main thing is that these things sum up, well, the vital thing is that they sum up to 1, all right? So you put that in there, and then you ask, well, what are the transitions of x as you take these weights? So we start out by maybe taking action J to begin with, and then you keep rolling forward. And as you roll forward, you're just setting up what is almost a Markov chain, because it's just, you're just taking these different probabilities of moving from one state to the next. Where when we're thinking about moving one state to the next, we're thinking about, well, what are these different weights that we're putting on actions? That different combination of weights is going to determine where things are going to go. So if we've got to here now, x tau, what's going to happen in the next tau plus 1? We're putting some weights on these different actions. We're hitting it with, well, what's the transition going to be? Go from there, and then you get, here is the kappa. In other words, suppose I start out with action J, and then I follow with this bunch of weights, and so really perhaps I should have a little omega up here to reflect the fact that I'm choosing a bunch of weights. Given a bunch of weights, and I start at xt, what will the distribution of x tau plus 1 look like? Say it one more time. Start out with action J, okay? It's going to push me in these directions, okay? Then, when I get to here, I'm going to look at my weights, and I'm going to say, well, if I reach here, this is the set of actions I'm going to take. If I reach here, this is the set of actions I'm going to take with the weights, okay? Then that'll tell me what is the distribution of my state variables the next period. Here it is, right here. Next period. Keep rolling like that, okay? That's all this is doing. It's not hard. Could put it in matrix if we wanted to. What do we get out of it? Suppose we got weights, okay? We start out with the conditional value function. Here's the utility associated with the action J. We're going to put weights on all of this stuff over here that are going to push us out through these different time periods. Okay. We're going to get a utility here, plus we have to deal with these weights that I'm talking about. That's the we have to deal with these conditional value function corrections that I was talking about before, as the size. The weights we're picking ourselves, we're allowed to pick any set we like, subject to the fact that they're summing to 1. And we can always write down the conditional value function in this way, okay? You still do maximum likelihood if you wanted to do this, because all you do is plug in for each of these P's the rule that gives you those conditional choice probabilities, right? Okay? I'm saying don't do that. There's going to be difference of opinion about that. That's okay. Depends on the problem. So you can still do this, okay? You can plug in here. And so this is, again, an identity. It's just a way of representing the conditional value functions. And it's exploiting the fact that we're already assuming when we set up the model that these people were behaving optimally. And so we're getting some information out of the fact that they make these different choices with different probabilities. It's telling us something about what their preferences must be. And in fact, it's the only information we have. Those conditional choice probabilities, along with the transition matrices, fully describe in a sufficient statistic way what we know about the problem, okay? So in thinking about this construction, which is really what it is, it's actually telling us how to think about the conditional value functions without doing recursive maximization. Because if we can plug in these conditional choice probabilities or estimates of them in here, then we've got the conditional value function straight off. There's no magic involved. It's just pointing out or using the fact that in any event, we're going to exploit the fact that these people have already solved the problem for us. That's what we're assuming in our model. So why are we using the computer to do it again? Okay, that's the intuition. So as we move forward, we could then ask, well, what about those flat regions we were talking about? Is this model really identified anyway? Because it's important to recognize that maximum likelihood is not an identification theorem. It has nothing to do with identification. It's well, not quite an algorithm, you wish. It is a criterion function for choosing a point or a bunch of points in the case of maybe something that's set identified, and then you'd have to think about how the maximum likelihood estimator was defined in that case, okay? Is this model even identified, or how much of it is identified? So let's start out. Let's suppose, assumption, again, all right? Remember, we start out with the model, we see where it leads, we say this is our prediction based on the model. I'm sorry, my assumption's not very realistic, but you come up with a set of alternative assumptions that make more sense, and then your prediction will be taken more seriously than mine, okay? That would be the way I think we should play this game, all right? And that's exactly what I do in consulting. So you guys go ahead and do your reduced form stuff when you're consulting and you come up against me. I'm going to ask you, where is your model coming from? That's what I'm doing right now. Not against you. Hopefully never. So here we have it. Suppose we know the time horizon could be infinity, stationary. We know beta, okay? We know what the form of the transition is. And here that's not really important because we already know this one's identified anyway. Because we've already made the assumption, the conditional value function, conditional, the independence assumption, conditional independence assumption, that the transitions only depend on your choice and the x's. And so that one is identified for sure, non-parametrically, given the conditional independence assumption. The G, we're going to assume is type 1 extreme. We don't have to assume it's type 1 extreme, but we assume we know it. Not just know it up to a parameter, but know it, all right? If we don't only know it up to a parameter, we're going to see that we have to know something else instead in order to identify the model, okay? You want to relax something? Well, you got to give up something sometimes. And then here's our U. We're going to assume that T, beta, F, and G are known, but we're asking under what circumstances is U identified from we're seeing the background variables and the choices that people make along with the conditional independence assumption that we're making. Okay? First point is widely believed, and I would say probably true, that U is only identified relative to one choice per period for each state. Can we say more than that? So for each time period and for each set of state variables or value that the state variable can take, let's fix the utility that you get from one of the actions and call it C. In other words, we're going to say, let's assume we know for a minute the utility that you get from one of the actions in any given state of the world. I realize we don't know that. Let's assume that for a minute so that I can make my point. And let's construct our transitions such that we're repeatedly taking this, what I'll call normalized action. Typically, we choose a normalized action to be something like action 1, in which we say the utility from action 1 is 0. Okay? That is what we often do. And I'm not saying that's a great idea, but that is, in fact, what we often do. And so what would happen to the state variables if we always took that normalized action? That's what that K star is telling us, all right? What do we get? Well, basically, we get a kind of an observational equivalence theorem, which says that, and the easiest way to see this is just to fix R equal to T. Let's not worry about the convergence aspects of this for now. Suppose we fix T and we say, okay, we'll define this U star that way, where we're adding in the utility. We start out with the real utility, and then we add in our correction factor, and then we subtract off the real utility associated with this normalization. And that's done for the very last one. And then for all the intervening ones, again, what we're doing is adding in some utility that we've made up for the normalizing action. That's what that C is. We make up a utility and we say, suppose it's this, suppose it's that. Often we'll say, suppose it's 0. And then subtract off the real utility that you get from that normalizing action. But you don't just do it for the current one, but you've got all these corrections that go on down further down the line. And here's the kicker, that you're really taking into account, well, if you're fixing a utility at a certain amount, well, it doesn't just affect the way you infer stuff for now, but in doing that, you've got to imagine that the person, or that it's going to have consequences down the line. Because you're also making an assumption of what's going on down the line about their utility. Could be wrong, okay? That's going to affect the conditional utility, the conditional value functions, because you're normalizing all the way through. But suppose you did that, then what we can say is that this thing is observationally equivalent. In other words, this construction will yield exactly the same probabilities as your true utility function. Let me rephrase this. You start out with a dynamic model, okay? You set your U's, you set your G's, you set your T. You now have a fully specified discrete choice model. Your agents in that model solve that problem, okay? They solve that model. that leads to conditional choice probabilities for that model. Now we ask, could those set of conditional choice probabilities be generated by some other model? Answer, yes. What properties would that model have? Answer, well, you can add one normalizing utility per state, set up your other ones that way, and then it will yield the same data generating process. Okay? So that's the sense in which these models, even with the G specified, yield some observational equivalence. Because after all, you only observe choices. Yeah, I'll get you. You only observe choices, not levels of utility. Yeah, go ahead.
Is this different from saying that choice ordering is invariant under affine transformations?
This is not necessarily an affine transformation because you're picking a utility. Well, maybe it is. In this larger space, yes. I think that's true. Subject to that, suppose you normalize, okay? Suppose you do what I've just said. And then we ask, can the rest of it be identified? The answer is yes. In other words, providing we normalize one of the choices, say the first, then U is identified. Okay? So the easiest way to think about this again is to go back to static models. Say, okay, in a one-period model, I not only have to say what the equivalent of G is, the disturbance, the probability distribution of G. I not only have to, but I also have to say, well, I'm going to normalize one of the choices to be, say, 1 or 0 or whatever. And then I can get the rest. Okay? And then in the dynamic setup, you have to say just a little bit more. You have to say, wait a minute, I also have to assume what beta is as well. And so if I relax any of those things, I don't know what beta is, or I don't know what G is, then what I have to do is start imposing assumptions on the relationship that the observed variables have on each other in terms of the utility that the person gets out of them. Well, the model's exactly identified. And that means you could estimate the conditional choice probabilities, put no structure on them. If you didn't put any structure on them, you'd get the maximum likelihood estimators for the CCPs. You'd estimate the transition probabilities. Okay, the transition probabilities, again, if you didn't put any structure on them, or even if you did, you could talk about the maximum likelihood estimators on that. And suppose you didn't put any more structure on that, you've got as many CCPs as you have U's. And so if you put that all together, well, then you would actually have the unrestricted maximum likelihood estimator for the U's. Okay? So one more time. You're estimating the CCPs, putting no structure on it. One-to-one relationship between the V's and the U's and the P's. Okay? Given the F's. The F's, you're estimating with a frequency estimator, just the same way as with the P's. They're both maximum likelihood estimators. Nothing very, very simple. Establish that. Nothing left. You now get the U's. We've just shown what the representation of the U's is. Okay? In terms of once you normalize one of the actions, all the others come out, drop out that way. That then gives you what I'm calling the U being, it's exactly identified. So it's clearly consistent, asymptotically efficient, Cremier lower bound. What's the significance of that? It means automatically that the only reason why you can get something that is more efficient than that is to impose assumptions on the U function. Nothing wrong with doing that. Everyone does it, okay? I'm not suggesting that's a bad thing. But what I am saying is that the gain that you get in efficiency comes solely from putting assumptions on the utility function that you're using. And so obviously you'd like to be able to justify that if you can. And that's something that we think about when we're doing the applied work, and it's reasonable. The problem is if you don't impose these kind of utility, if you don't impose those kind of assumptions on the utility, well then obviously you've got as many utility terms as you have conditional choice probabilities. That's a lot. We already talked about, what, 90,000 or something when we talked about the very beginning example of, you know, how many kids, how old, and what kind of education do you have when you're thinking about, well, the choice probabilities. So that's the argument for putting functional form assumptions on the U's. I'm still not quite sure that's the way to go, by the way. Because ultimately what we're concerned about is not so much the utilities themselves, but in terms of the choices, in terms of what would happen under the counterfactuals or the elasticities or something like that. And so I don't know where to apply those restrictions, because often we're just concerned about aggregate statistics relating to, well, what's going to happen if we change this environment? We're not going to go through all the conditional choice probabilities for every single person as to what's going to happen to him or that kind of person. We'll be averaging over different groups of the population. And so then that raises the question as to where should we actually be doing the restrictions? And I kind of think that's a little bit of an open question. But let's move on. Actually, what people do, of course, is, and I have got till 12:15, right? Theodore? 12:15, is that correct, or Bertel? Yes? Yep. Good. Thanks. In practice, what we all do is say, let's make the utility of X depend on a relatively small number of parameters. Okay. Let's look at the transition function in terms of, again, a relatively small number of parameters. Parameterize all that. And then assume that the data generating process comes from what I'll call one of these models. In other words, a model in which there's a particular theta 1, particular theta 2, everyone's solving their problem subject to that. And we're trying to find out which one of the thetas it is. We'll call that theta 0. All right? Often, we will assume that the utility, is there a problem?
No.
Oh, I see. The utility is a linear combination of X. No, don't change me. Doesn't like that slide. No. Linear in X doesn't depend on T. That's a typical type of assumption, all right? The utility depends on state variables, but nothing more, and it's often linear. Think of a labour supply equation. You know, what do wages depend on? Step it out. Or sometimes we'll even assume that this is degenerate and follows a deterministic law of motion. You know, things will increase by 1 or 2 or stay the same depending on what choice you make, all right? Yeah. So one way of going about it, this is quasi. And this is what I went through with at the end of the last lecture. All right. Go ahead, estimate your transition density for the x's conditional on your actions. Okay. Put together this path saying, well, suppose you follow a given path, how do your x's work out? And that's going back to that representation of the value function where I said, well, the value function can be written in terms of utility plus correction factor plus following period plus correction factor, et cetera, et cetera. Put that thing together. Start substituting in these correction factors after we've got the p-hats, cell estimators in there, and then the log p's for the type 1 extreme value. I said when you got type 1 extreme value, it was just log of frequency of that choice. And then I said for a nested, you just average over the choices, and it's a weighted combination of those two. And then put together a V with a V hat where we're using the estimated transitions for what goes on in the F, and we're also thinking about how to put together this conditional value function, which I talked about before. And then go ahead and instead of putting in Vj or V hat, you use the P's. So just with respect to the last couple of steps now, here's our estimated conditional value function. All right, this is going to be our estimated conditional value function. We're not going to solve, we're just going to put in P's in the right spots. Well, it's equal to the U. Okay. We're going to estimate that part. And then there's this stuff left over that's related to the dynamics. This is why, in other words, this is why the model is not a static model, because you got the H hats in there. It's really an H estimated by H hat. And that H hat, in the case of where we're normalizing the utility number 1, in other words, utility from the first action equal to 0, and then we're always taking the first action out, all we're doing is putting in the correction factor for the next period, the correction factor for the following period, et cetera, discounted out, summed, and then taking into account of where you might go, all the way to cap T. Similar thing if you're going to infinity, okay? And so in a type 1 extreme value, basically what we have is, well, exactly what we have is this utility associated with current action, whatever it is, J, added in with the H. This is the estimated continuation value. It's like almost a continuation value because it's the beta big V part. That's what's going on there. And then we've just substituted in the right spots the fact that this person is making the choice 1 all the way through when that is not optimal, okay? So that's why we need a correction factor in there. And then do a logit. So estimate the P's, plug it in here, these are log P's, hit this with a discrete choice, hit this with a logit model, and you're done. It's one way of going. Another way of going is to say, okay, why don't we look at this vector function just by stacking the difference between the different correction factors associated with the choice J. Okay, that would be another way of going about it. This is basically saying, let's form the difference between the utility from taking action J when I've got my theta parameterization versus the utility that I get from not putting any parametric structure on the model at all. All right? So this is sort of what minimum distance does, right? You take some kind of what we'll call reduced form, which is really a reduced form, not something that someone made up, but it's reduced from the structure of the model. And the reduced form in this case are the utilities that you form without putting the theta structure on the U's. We already talked about how to get that, right? So we now look at the difference between the utility that you get when you put the parametric structure on minus the utility that you get when you don't put the parametric structure on. You've got that for all the different utilities, all the different states, all the different time periods. And then say, how close can I make that to zero in a, say, a Euclidean norm, say, squared, summed, go from there. One of the advantages of doing this is that this is something you put together without putting any parametric structure on. So this is a number, okay? This thing here is just the utility from x and theta. Well, often you're assuming that's linear, right? You're saying little u is equal to x beta. That's what you often do in a discrete choice model, okay? And so now you've got x beta minus number prime weighting matrix, same thing on the back, least squares, all right? And so that's the sense in which this least squares estimator is even simpler than the maximum likelihood. Don't have to do a logic, just go straight from there. Yet another way, you could use simulated moments estimator. And in this case, what we'll do is just say, okay, why don't we just simulate the x forwards using the f and the p and a given action. And the reason it's worthwhile pointing this one out to the following. Notice that when we do this, we're just looking at the conditional choice probabilities and the transitions. We are not making any assumptions about the unobserved variable at that point when we simulate the lifetime path forwards. See that? Because we're basically saying, here are our x's, then we just move forward, we see the conditional choice probabilities, we move forward again. Nothing about the g. In other words, nothing about the distribution function of those disturbances. Here is where we make our assumption about the g. We're talking about what is the conditional expectation of the epsilon or the unobserved variables when you take a given action which is optimal, okay? That's what we're doing then. And that's where we need an assumption on the g. That is exactly where it comes in. And this is kind of getting at the difference between almost discrete choices versus continuous choices. Because when we're looking at continuous choices, it's just a derivative and it's right next to each other. But when it's the discrete choices, we sort of don't know what's going on in the middle. And so so we lose a bit of information there. We only see the choices. We don't see how far those choices are from each other in terms of utility terms because we don't see the unobserved variables. It's a very loose discussion. Sometimes I think this lecture should not be recorded. But in any event, this is where the G comes into play, okay? This is where the assumption about G really comes into play. So you stitch together this lifetime utility just by putting together the U's plus the expected value of the epsilons, and then you just compare with what people have done, and you go from there. Again, you can use any old set of instruments because in your model, all the past stuff can be used as an instrument given the conditional independence assumption you've already made. And so then again, you're going to have a quadratic, and providing these, it's not obvious from this, from what I've said here, but if you've got this stuff being linear in the utilities, the whole thing will end up being linear. And again, you get a closed form solution in that case too. All right. In the remaining 25 minutes, I want to go through one more application, which is a little bit more recent, and sort of so you can sort of see some kind of example of how this stuff can be applied. Because I'm figuring that your concentration is lagging by now. Mine might be too, by the way. This is what's happened in the US population in terms of fertility. Well, a little bit, not just that, but first, well, fertility, you're seeing average age of mother at first birth, 22 in the 70s, 24 a couple of decades ago. I say currently 26, depending on your education level. It's even higher, okay, 30s, if at all. So, and then if you look at home buyers, first-time home buyers, 28 in the 70s, 30s in the 90s, now about 32. Okay. Not really. Actually, it could be even higher than that by now. Actually, New York, I believe the New York Times, 40s. I don't know whether that's really true, but you know, it's up there. And then if you look at labour supply participations, going up 48%, 75, 74, see that jump? Hasn't stayed, more or less, it hasn't quite stabilised. It's more than 76 now, but 76 in 2015. So that's sort of what's going on. And demographers see this as a, quote, problem. In fact, they're arguing, gee, is the world population going to kind of atrophy? Right now. I'm not convinced that that is a particularly good way of thinking about things, but certainly it is a topical problem within demography right now. No question of it. Conferences and stuff. So if you're looking at what's going on in terms of the graphs here, you've got these circles being the average age at first birth. See? And then you've got the stars, average age at first marriage, and they're practically on top of each other. So it's really hard. This is only the mean, mind you, but they're very closely related, no surprise. You've got the labour supply participation, and that's on this vertical axis here, with age on the horizontal, okay? And you're seeing, so what's going on here? In the 1970s, you'd drop off while you had a kid, and then sort of come back, not so much. By the 1990s, there's not much of a change here, but then go up to a little bit further up, there's another increase after your childbearing ages, okay? And so at the same time, when you're looking at the house purchase, it's going from here in the 70s, 80s, 90s, 2000s, okay? So everything's moving together like that, all right? And so you would think maybe they're related, perhaps. So, and why would that be? I haven't got the slide, but if you look at the second birth for families that have 2 or more births, and you look at when they buy a house, they're just going up almost the same age in terms of means. And so one really simple-minded story is saying, well, why do people get married? Because they're kind of committing to some kind of dual care, joint care of the kid that's about to come. I mean, they're together after all. And why do people buy houses? Well, it's about the time they settle on what size family they're going to have, so they want to know how many bedrooms. Okay, so that is a very simple story of what's going on. But we can sort of formalize it in slightly more general terms, thinking about that stuff, because it isn't just the house size, of course, or the purchase of the house, but it also probably has something to do with geographic mobility and where your kids whether you want to move your kids around to different schools in different locations. And when I say kids, I really probably should say kid, because for much of the developed world, and certainly for educated people, very highly educated people, it's either 0 or 1 now. What happened over these four decades? Real wages rose, real interest declined, housing prices rose and then fell. Females became more educated. Okay. And you can see that schooling going up, wages going up. These are actually standard errors on a wage regression. Housing prices sort of going up, but whoa. And then if you look at the interest rates over this period, and this is the period we're looking at using PSID, here's your home ownership according to the census going up and down, okay, in 2 different age groups, younger age group, older age group, and then over the years, okay. And here are the T-bill rates, and notice that. Interest rates going up, home ownership going up, which is contrary to everything that the media talk about. But that's what the census shows. That's what the T-bill rates are. So, non-stationary model, clearly non-stationary. Okay. With fertility, female labour supply, and first home purchase decisions. In this world, and not just in this world, but in the US, people getting out of home ownership is pretty constant over this period. So almost all the change in home ownership is people buying them later than before. That explains probably 95% of change in home ownership rate, home ownership. Non-stationary drivers, education, wages, interest rates, housing prices. Going to use the PSID and then do some counterfactuals, ask what happens if one or more of these things didn't change or did change? What would have happened under those circumstances? So basically, estimate the model and then ask what would happen in a different world, okay? So you've got a birth in one period or not. You've got non-housing consumption, which is going to be a continuous choice, but we're going to have exponential utility over that continuous choice. And as a result of that, we're going to be able to solve out to get the indirect utility from the optimal consumption choice and won't have to worry about it. Okay. We've got whether you're in the labour force or not. And here we're only looking at females, so we've dropped off males altogether. They're just an appendage. And then you've got, did you buy a home in period T or not? So whether you own a home or not, it's just going to be given by, well, did you buy a home beforehand? There's a little bit of selling off at the end, but not that much. And we're really tracking what goes on between like 20 and 45, so hardly any. People are changing homes over that time. Not that much, but some. And so we deal with the change in homes, but not with the choice to change in homes. That's how we're thinking about that. These are the choices that you've got if you haven't bought a home already. 8 of them. Either have a birth or not, work in the labour force or not, buy a home or not. After you've bought the home in the model, just effectively 4 choices. Have another birth, do you work in the labour supply or not? Okay. And then for each of these choice permutations, we've just got these different J's. Go from there. And we're going to get some household utility. Well, want to focus on, first of all, births. When you have a kid, you're stuck with it in this model. You can't get rid of it. It's not like a durable good like a car. Can't sell it. You've got it. I know. So in the, I shouldn't say that. It's still on the mic. Point being that you don't get very much more information as an econometrician or as a person about the utility that you'll get out of that kid. Because you make a lifetime decision right there. I'm going to get that kid and then it's going to be with me for the rest of my life, probably. Okay? You actually hope that. And so you're thinking about, well, what is the expected lifetime utility that I will get from that kid? And so there's no way econometricians can talk about the terrible 3s and the cooperative 10s and 11s and the painful teens. You can't do that because there's no way of seeing how people react to how that goes on, or unless you see how people react. Some kids are more terrible than others. Unless you see how people react, you're not going to get variation, and so you won't be able to infer anything about what happens, the utility to get at different age groups. Yeah. So when you're thinking about these kinds of models, that's important to take into account. What kind of variation do you have when you're modeling this stuff? So you get some lifetime utility associated with having a birth, and that birth and the lifetime utility will of course take into account the number of kids that you've already got and their ages. Maybe there are scale economies. I'm not sure about that. Maybe not. The point is, it'll take into account the number of births that you've already got. It won't take into account the number of births you're going to have because you don't know yet. You're living in an uncertain world. It's going to depend on the observables and, in this world, the unobservables as well. Okay? And actually the same with a house in this kind of setting, because in this kind of setting, once you buy a house, you stick with it. And the reason you're sticking with it is not because I believe that you can't get rid of a house and go back to renting, but because it doesn't happen that much in the data set. Somewhat, and to the extent that it does happen and we're not taking into account, the model is being misspecified. Sure. It's probably being misspecified in a lot of other ways too. So, and then you're going to get this labour supply thing. That is going to be current utility, could potentially depend on past work, both in terms of how easy it is to do domestic stuff. It's also going to affect, obviously, your wages, but that's a separate issue. And then consumption. So that is essentially the utility function that you get out of this. Okay. And we're parameterizing each of these pieces. And so a bunch of things. What do you get out of housing? Well, it depends on whether you're working or not, depends on whether you're having a kid or not. And both of these things and a bunch of other stuff as well. To reflect the fact is, do I want to buy a home at the same time as I'm working full-time and having a birth? Maybe not. So you would think the coefficient on that, on buying a home at the same time as you're having a birth, is negative, right? And you can imagine there are a few other coefficients that are either positive or negative, depending on what else you're doing and also your family background. Okay, got no kids, or maybe having another kid, not so important. And then on this side, we're talking about, well, even things like, are you married or not? We're not making marital status a choice, but we are letting it vary as a stochastic process, okay? So you can, and here I want to distinguish between things you ignore entirely, things you put in as some kind of stochastic process, but you're not having choices over, and things that you're having choices over as well. So you've got to make all those decisions as you sort of head down the, here's my model world, and what do I think I'm going to get out of it? And obviously, the more stuff you have in it, well, that's good on one side, but on another side, it's more variation with a fixed number of data points. So there's always that trade-off. Well, there's a budget constraint, of course, and that budget constraint is just given by what happens to your income, depending on your non-labour income, whether you buy a house or not, and and also your wage income. And that then gives you a law of motion, which determines what kind of wealth you have each period. You go from there. Okay. In this setup, I'm just assuming there's an interest rate. You can borrow and lend at that point. And there's a kind of question here as to whether that's a good assumption or not. Remember, though, that when you're buying a house, a lot of it depends on your collateral. The house itself is collateral, so a lot of it depends on whether the bank thinks you can pay the money back or not. Yeah, go ahead. Yep, sure you can. Which one?
So the coefficients of each, the first one.
Yeah.
Theta 2.
Theta 2, whether you have a birth or not.
Gamma 3.
And gamma 3. Yeah. All right.
Joint impact on utility when you both have a house and also the fertility.
Right. Okay. It's important to recognize, though, that we don't have choices conditional on, parameters that depend on each state. And so when we went through the identification problem, we had a utility function that was dependent on the state and the age and everything else. And that's how we got it. That's how we got exact identification. This one has lots of, shall we say, restrictions in that we're only putting the same coefficient regardless of the state, regardless of ages and stuff like that. And so that, if you like, linear functional form is already imposing a ton of restrictions. And so that's how we can get that kind of identification. Now, that's not formally proved, of course, but all I'm saying is that there are way less parameters than there are state variables in this setup. Okay, so rolling on. How well does this model fit the data? Just to very quickly point out that the owners are slightly older than the renters, education slightly more, here's the number of kids, more, here's the ownership rate, labour force partition rate is lower for owners versus renters, as are hours worked, but on the other hand, the labour income is higher. Okay, so this gives you some idea of what the PSID looks like. That's the panel that we looked at. I'm not going to go through the estimates, but they are standard, quite reasonable. There's nothing counterintuitive about them. What I want to do is just look at the fit, just briefly. Here is the fit across ages, because you really got two things you're kind of concerned about fit. One is how well does it do across the different ages, across the life cycle? And the other is how well does it do across time? After all, we're looking at about 30 years. And so we'd like to see both the cross-sectional and the time series properties of this. Remember I said before, there's really no difference between macro and micro. In other words, we should be actually taking over what macro does. Okay, so here's our here's the model at different for different ages. Okay, the data and then the model. And one of the main thing that I want you to point out here is we're not too good on the early ages, and that I found in other data sets too, and it's basically a reflection of the fact that we just don't have enough data on early ages in the PSID, especially when we're talking about fertility, because not very many people are having births, and even the ones that do are very selected group. But it's not the only place we're missing. We're a little bit missing up here as well. This is the average home size. Now, the average home size is not something we're even modeling, but we're just tracking, okay? And the fact that the data gets a lower average home size towards the end and a little bit higher towards the beginning is more a reflection, I think, of the data saying, yeah, some of these people move from their big homes to their smaller homes once they become empty nesters. And so that could be explaining what's going on there. We haven't really checked it out that closely though. Labour force participation rate, again, you've got the model going like this, and the data is much more kind of even. So there's kind of a question about that one too. And here's the data on children, pretty good in terms of family size. Births, not so good, okay? And there's no surprise there, because on the flow, the birth one period or the next, you know, you're not going to pick it up that well. But if we're talking about the number of children, well, then some people are going to be having births a little bit early relative to what they should in the model, and other people are going to have late relative to what they should have in the model. Of course, I'm acting as if that they should follow the model, but why that's true, I don't know. But in any event, that's why it'll go both ways, and that's why you're going to end up with a stock more or less right, even though the flow not as good. So you can see what we kind of cheated there by putting children in. Over time series, if I can get that, here we go. Here is home ownership rate. And what I did was to put in the census rates, okay? Here's the census of squares. And you can see the model actually does better than the PSID data. And that's a little bit weird too. But because it's the PSID is, which is how we estimated the thing, is decidedly lower than what the model predicts. But on the other hand, it's closer to the what the census does. Again, with the home size, we're a little bit high here, but basically the right trends. And labour force participation, more or less tracking, and likewise children, except we're a little bit high all the way down. Okay? Yeah?
Have a sense of how much difference between the census data and the PSID is sampling error?
Say one more time.
Do you have any sense of how much of the difference between the PSID and the census data is sampling error?
Yeah, we do. And so when we did our counterfactuals, we rebalanced the PSIDs to be able to reflect accurately what the population was doing. And now the way we get a sense of that, of course, is to look at the census at these 10-year spots and then compare what the PSID does. And of course, these are exactly those differences in these at those points. Now, we did a little bit more than that, but and in rebalancing, we did a better job. But that gives you some sense. So I haven't bothered to put in the census one here, but fairly close and nearby.
The idea is that it's mostly about the survey weights being wrong, essentially, like wrong being.
not fully reflecting the US population due to attrition and stuff like that. And also the way the PSID samples, which is through descendants, of course. And then there's kind of question of, well, is that a good way of thinking about how we're moving?
The estimation uses those survey weights?
The estimation is at an individual level and it's off the PSID.
Yes, but it uses the PSID weights in estimation, or are the weights ignored?
The weights are 0 in the estimation, but when we do the counterfactuals, we re-weight the population that we're starting with to get the counterfactual. So it's important in this stuff is you take the survey or the panel data that you got, you estimate it off that panel, which is going to be unbalanced relative to the overall population. You come in there, you get your estimates, and then you ask, what's going to happen when I re-weight to get the population? Absolutely. And in fact, that's exactly what I was describing here. So the rest of you can take a big sigh of relief because I've already explained this slide. But it was a good question. It's exactly the right one to ask, as you can see. Because PSID is unbalanced. And so we've got to take that into account. But there's more to it than that. In that population, the real population, the sample population, these guys are taking into account the future, which is it's non-stationary. And so how do I want to do my counterfactual? Because the people that are being sampled later on are looking to stuff that's going to happen outside of my sample. And so I won't know what the aggregate shocks were. And so what we did when we were doing the counterfactuals, we said, okay, let's suppose these people live in a stationary population. Let's suppose they live in a stationary population, okay? And then forget about migration and stuff like that for a minute. And then ask, how do these different effects work out then? I don't really see how to do anything else. You don't have to do a stationary population, but what you do have to do is state what the aggregate effects are going to be or the distribution of the aggregate effects, and then go from there. And we obviously don't have the distribution of how those aggregate changes occur because we've only got it year by year, and that's not very many observations. And that's a pretty fundamental problem that economists are going to face across the board as you try and figure out how are people going to behave in a different counterfactual regime when you know very well there are going to be all kinds of aggregate variables that are affecting what's going on. And it's very hard to get a good handle on how people think about those. All right, just to clean up for a minute. So first of all, we generated an artificial population of 23-year-olds, reflecting the population. Population distribution, okay? But within that, set their preferences to our estimates. Then we just went ahead and asked what happens if you apply the optimal rule for 25 years. So we solved it, okay? Go from there. And actually, the aggregate statistics for that benchmark stationary economy are actually very close for the US economy. And then we said, well, start out with a benchmark economy at 1991 values. Go from there. Here are the basic results. We've got charts and things, but this is good enough. Suppose you compare the stationary economy in 1971, but you said, okay, let's let the base wages increase to the 1991 level, double their 71 level. What would happen? Home purchases postponed, labour force participation increases, births fall. No surprise, okay? Not only that, by the way, you could say, well, let's not do the increase it to the, let's not just look at the stationary distribution of what happens. You can actually look at it year by year, and we did. It's just that it's boring because it just creeps up to that level where it converges to. So it's not worth talking about. Suppose you increase in educational attainment by 1.5 years, which is about what it increased over that time. First home purchase goes forward slightly. Labour force participation increases, birth falls. Okay. Suppose housing prices increase by 15%. First price, home purchase postponed, labour force participation slightly increases, birth barely affected. And then we also looked at the interest rate, and it actually increased, and you bring your home purchases forward here. It's a durable good. You want to save more. That's what really housing purchases do. Got a higher interest rate, so that's why you do it. If the house prices are not increasing at the same time, you put more in tomorrow's consumption than today's. And so you get labour force participation falling, births increasing. So that gives you some idea of the kind of stuff that you can do with these kinds of models. But we're all going to say a lot about this in the next few days, and it's time to have lunch. So let's stop.